Hello everyone, and welcome to Lesson 9. In this section, what we'll be doing is covering the two homework questions from the previous section, as well as moving on to one more, slightly more advanced question. It's more advanced in that it's not in the natural language laid out as clearly as some of the questions we've been doing in the past. It's a little more realistic and a little more similar to what we might experience or what we might see in real life. So, to begin, let's look at our homework questions from last time. The first one, Chapter 2, Problem 4 from the textbook. A carpenter makes tables and chairs from wood and fiber. The store has 50 units of wood and 40 units of fiber. Each table requires 10 units of wood and 4 units of fiber, whereas each chair requires 6 units of fiber and 4 units of wood. The store has to use a minimum of 20 units of fiber. The demand for tables is no more than 2. Each table is sold with at least 2 chairs. A table and chair earn the store $300 and $200 in profit respectively. So this is our basic question. As always, we're going to follow the same steps. We're going to review the question. We're going to highlight key information, focusing on our decision variables, our objective function, and our constraints. So let's begin. A carpenter makes tables and chairs from wood and fiber. So we have tables and we have chairs. This seems important. We also know they're made from wood and fiber. So we know already what we are making. Most likely, because it's a production question, most likely what we are making will be our decision variables. So most likely our decision variables will be tables and chairs, but it's not clear totally yet. The store has 50 units of wood and 40 units of fiber. These are essentially ingredients for tables and chairs. Because they are ingredients, we have a limited amount. Because we have a limited amount, they are most likely going to be our limitations. So wood is most likely a limitation. We have 50 units. Fiber is most likely a limitation. We have 40 units. Each table requires 10 units of wood and 4 units of fiber. Each chair requires 6 units of wood and 6 units of fiber and 4 units of wood. So we see here again that from our limited supply, we are now using resources. And because we are using resources, we have limitations on how much we can use, and that will most likely impact our decision-making process. The store has to use a minimum of 20 units of fiber. When we see the phrase minimum, we generally assume this is another limitation. It is the smallest amount we can use. If we use less than that, we do not have a valid solution. The demand for tables is no more than 2. So again here, we have another situation that tells us what we must do, what we cannot do. In this situation, we cannot sell more than 2 tables. If we sell more than 2, it is not a valid solution. Finally, each table is sold with at least 2 chairs. So if we sell a table, we have to sell 2 or more chairs with that table. we cannot sell less than 2. So here, essentially, we assume we've covered most of our constraints. Finally, a table and a chair earn the store $300 and $200 in profit, respectively. So we see here that this question is relatively straightforward. All of the information essentially given to us was critically important. There's very little information that is not highlighted in red. So what we have now is the key points. To continue to the next stage, we now have to determine where those key points fit into our solution. The first step we need is our decision variables. And we see that we're making tables and chairs. We know a table earns $300, a chair earns $200. So our first decision variable is our table. X1, as always, is equal to tables. And that's actually the number of tables produced. X2 is chairs. And that's the number of chairs produced. So we know once we've found our decision variables, we have to connect our decision variables to our ultimate goal. We don't have the ultimate goal stated in the question. So we have to use common sense in this situation. So here we know that we are we are manufacturing something. We are making tables and chairs. And we also know it's a business. If they're making something, most likely, and we're talking about how much they make per item, we're mostly talking about maximizing their profit or maximizing their revenue, because we know how much they earn down here. So in this situation, our objective function becomes maximize Z, which is revenue, and that's equal to 300 x1 plus, and that's revenue per table, plus 200 x2, and that's revenue per chair. We'll just make this a little simpler. I'll just eliminate these spaces so we can stay on the same line. So our revenue, we're trying to maximize Z is equal to 300 x1 plus 200 x2. So we've completed our objective function. We've related our decision variables, how many tables and how many chairs, to our ultimate goal, determining revenue, because we know we get $300 in revenue per table and $200 in revenue per chair. So our next step is going back here and looking at our constraints. Our first constraint, we have 50 units of wood. Our second constraint, 40 units of fiber. And we know it's 10 units of wood and 4 units of fiber for a table. Table is X1. And 6 units of fiber and 4 units of wood. They're reversed for each chair. So we come down here. Our first constraint is based on 50 units of wood available. So we come up here and we see table is 10 units of wood. Chair is 4 units of wood. Table is X1, so 10 X1. chair is x2, so 4x2. And it must be less than or equal to 50, the total amount of wood available. In previous questions, everything's kind of been carefully organized for you. In this question, we had some things misaligned, some things out of order. But as long as we remember x1 and x2, x1 being tables, x2 being chairs, we're able to correctly realign this information. And we see here as we move on to C2, which is the total amount of fiber available, is 4x1, which is 4 units of fiber per table, plus 6x2, which is 6 units of fiber per chair, must be less than or equal to 40. And that's the amount of fiber available. So we have our first two constraints, and we've used this information here. But we now have another constraint, a minimum of 20 units of fiber. So we have to come down here, and we have to list our fiber usage. So we go here, fiber. We already have our fiber usage right here, 4x1 plus 6x2. 4 units of fiber per table, 6 units of fiber per chair. So C3 is equal to 4x1 plus 6x2. And it must be greater than or equal to 20. And that's the minimum amount of fiber used daily. So we go back here, and now we've covered this. But we have another one. Demand for tables is no more than 2. So up here, we go back, and we say C4. We see that tables is x1. So x1 is less than or equal to 2. If x1 is 2, no problem. If x1 is more than 2, it's impossible. It's not a valid solution because that's the demand for tables daily. And our final constraint, C5, we have a fifth constraint. So we can see it's getting a little more complicated. Each table is sold with at least 2 chairs. So we saw something similar in our last class, but we see C5 is equal to, we can eliminate these equal signs actually. It's not really necessary. We're just labeling them for comprehension. So X, we know that X1 tables must be greater than or equal to 2x2, which is the ratio of tables sold to chairs sold. If we sell 1 table, then we must sell more than 2 chairs. If we sell 1 table, 2 chairs is okay. 3 chairs is okay. 4 chairs is okay. But we cannot sell less than 2 times chairs for every table sold. So going into the natural language, we've now covered all of the relevant information, and we've collected it all here. Our final step to solve problem number 1 from the homework is collecting all of the information here in the universal format. So max Z is equal to 300 x1 plus 200x2, subject to the constraints. First one is 10x1 plus 4x2 is less than or equal to 50. Our second constraint, 4x1 plus 6x2 less than or equal to 40. Our third constraint, 4x1 plus 6x2 greater than or equal to 20, because that's our minimum usage of fiber. Our fourth constraint, x1, is greater than or less than or equal to 2, which is our demand for tables daily. And our final constraint, x1, must be greater than or equal to 2x2. So we've taken our natural language problem, we've converted to the relevant information, and we wrote all of the relevant information here together in one place in the universal linear programming format. If you have any questions, as always, feel free to contact me by Cacao. Let's move on to question number 2. This is Chapter 2, Problem 5. The Pinewood Furniture Company makes chairs and tables from 2 resources, labor and wood. The company has 80 hours of labor and 36 board feet of wood available each day. Demand for chairs is limited to 6 per day. Each chair requires 8 hours of labor and 2 board feet of wood. Each table requires 10 hours of labor and 6 board feet of wood. The profit from each chair is $400. Each table, and this was a problem in the homework, and from each chair is $100. The company wants to determine the maximum or the number of tables and chairs to produce each day in order to maximize profit. So once again, we're in a situation where we have to review the question carefully and highlight key information. The Pinewood Furniture Company makes chairs and tables. So as we talked about in the previous section, chairs and tables will most likely be our decision variables. And they are made from 2 resources, labor and wood. So here again, most likely we have limitations. When we are manufacturing, our resources are limited. If it is limited, these resources represent constraints or limitations. 80 hours of labor, 36 board feet of wood. So here we're relating the maximum amount of labor we have. That's how much our limited resource that we have. And 36 board feet, that is the limited amount of wood we have every day. Moving on. Demand for chairs is limited to 6 per day. This is another limitation. So we know labor is limited, wood is limited, chairs are limited. It looks right now like we have 3 constraints or limitations. Each chair requires 8 hours of labor and 2 board feet of wood. This is using our resources to produce. Each table is 10 hours of labor and 6 board feet of wood. Again, using our limited resources, so that will enter into our constraint equations. The profit from each table is $400, and from each chair is $100. This is relating our decision variables to our ultimate goal of determining the number of tables and chairs to maximize profit. So we've gone into our question. We've carefully reviewed the key information. We've highlighted it. And now we have to interpret it so that we are able to properly collect all of our relevant information in one place. So as we did before, let's do one more time. The Pinewood Company makes chairs and tables. They want to determine the number of chairs and tables. So our decision variables very simply become x1 is chairs, and that's number of chairs produced. Let's see. Let's make x1 tables. It doesn't matter, both are okay, but because tables is the higher revenue, I'm just going to make it x1 tables. As long as all of your numbers line up with tables and chairs, x1 to x2, you would have no problem. x2 equals chairs, and that's the number of chairs produced. So we have our decision variables. In our objective function, as we stated, we have to relate our decision variables to our ultimate goal of maximizing profit. So we see here, when we move into our objective function, we're trying to max Z, which is profit, if we receive $400 per table and 100 x2, which is profit per chair. I keep spelling chair incorrectly. So here is our objective function. We're trying to maximize Z at 400 x1 plus 100 x2. Before we can do that, we have to go into our constraints. And C1, our first constraint, as we see here, is a limited amount of labor. We have 80 hours of labor. Chair is 8 hours of labor. Table is 10 hours of labor. So we come back here, and C1 is equal to 10x1 labor per table plus 8x2 labor per chair, and it must be less than or equal to 80, which is the amount of labor available. Again, we'll just make it very easy just to keep it all in the same line. And that's our first constraint. If it's 10 hours per table and 8 hours per chair, we must be less than or equal to 80 hours of labor. We repeat this process for our second constraint. We see here that we have 36 board feet available. Tables is 6 board feet. Chairs is 2 board feet. So we come back here, 6x1, and that's board feet per table plus 2x2 board feet per chair. We'll make that board feet over here as well as BF, because just to save space. And we must be less than or equal to the 36 board feet we have available per day. So those are our first two constraints. So we come back to our natural language question and we check, are there any other limitations? We see one here. Demand for chairs is limited to 6 per day. So chairs is x2. So our third constraint becomes x2 must be less than or equal to the 6 we can sell daily. So we'll put it in here. Chairs produced is less than or equal to daily 6. Daily demand for chairs. We come back here and we see now that all critical information has been accounted for. Our final solution will involve all of these key points. So to finish off the problem, we go down here, and as always, we write our final solution in the correct format. We're trying to maximize profit if $400 per table and $100 per chair, subject to the following constraints. 10x1 plus, let me just double check, 8x2, and that's less than or equal to the 80 that we have available. We repeat the process for 6x1 plus 2x2, and that's less than or equal to the 36 board feet we have available per day. Finally, x2, the amount of chairs, must be less than or equal to 6, which is the daily demand for chairs. So taking the natural language question here, we have now converted it accordingly into our final solution here, problem formulation here, that will allow us to solve this problem. Those were your two homework problems. We will continue momentarily with our first new problem, which is a next level problem formulation. We're going to work through it together. I'll be back momentarily to do that with you. Hello everyone, and welcome back to the second half of lesson 9. In this section, we're going to look at a new problem, one we haven't seen before, and it at the end will not look overly complicated. However, because the information is scattered much more widely around the natural language problem, it may be a little more difficult to interpret this and translate it into the mathematical model that we require to solve the problem. So this is practice problem number 4, and let's review together. A factory situated along the river Ganges discharges 2 types of pollutants from its tanning and dyeing manufacturing processes into the river. To remove pollutants from its effluents or discharge, the factory installed minimum discharge technology. This cost $25 and $10 to process a ton of tanning waste and dyeing waste, respectively. The technology removes 0.1 tons of pollutant 1 from a ton of tanning waste and 0.5 tons of it from a ton of dyeing waste. So 0.01 tons of pollutant 1, 0.02 tons of pollutant 1 from tanning and dyeing. In the case of pollutant 2, it removes 0.3 tons of dyeing waste and 0.08 tons of tanning waste from every ton of the waste processed. Since tanning wastes are more harmful than dyeing wastes, the factory plans to process more tanning waste than dyeing waste. The current policy is that the tons of tanning waste processed is at least twice as much as the tons of dyeing waste processed. The factory has to remove at least 25 tons of pollutant 1 and at least 35 tons of pollutant 2. How can they minimize cost? So, let's go through this and find our key information. The factory is along the River Ganges, 2 types of pollutants from its tanning and dyeing manufacturing processes. So we know that it has tanning processes and dyeing processes. To remove the pollutants from its effluents, the factory installed minimum discharge technology, which cost $25 and $10 to process a ton of tanning waste and dyeing waste, respectively. What this tells us is that because we're relating cost to decisions, we now know this is related to our objective function. Because it's relating cost and decisions, that becomes key. So we know we have this relevant information. The technology removes 0.1 tons of pollutant 1 from a ton of tanning waste and 0.0 tons of tanning 1 from a ton of dyeing waste. So we now know from tanning and dyeing, it's removing both pollutant 1. In terms of pollutant 2, it removes 0.3 tons of dyeing waste and 0.8 tons of tanning waste from every ton of waste process. Again, critical information. Since tanning waste is more harmful than dyeing waste, the factory plans to produce more tanning than dyeing. The current policy is tons of tanning waste processed is at least twice as much as tons of dyeing waste processed. So another limitation on our decision making. The factory has to remove at least 25 tons of pollutant 1 and at least 35 tons of pollutant 2. So again, that is our third limitation. How can they minimize cost? So we've highlighted all the key information. Now we have to go down here and collect it. Let's look at the first section, tanning and dyeing. So these become our decision variables. X1 is tanning waste. And that's amount of tanning waste processed. X2 is dyeing waste, and that's amount of dyeing waste processed. In our objective function, we have to relate both tanning and dyeing waste to cost because we're trying to minimize cost. We see that all of the relevant information is right here. So now we have to write our objective function. If we are trying to minimize z, and that's cost, is equal to 25 x1, which is tanning waste, plus 10 x2, cost for dyeing waste. And again, we'll eliminate this just for simplicity to keep it all on the same line. Okay, so we've now got our decision variables and our objective function. Constraints is difficult only for one reason. The information is scattered throughout the natural language problem. We're going to go here, and we're going to see that the technology removes 0.1 tons of pollutant 1 from tanning waste, 0.2 tons of pollutant 1 from dyeing waste. Then we have to go down here, and we see that we have to remove at least 25 tons of pollutant 1. That's our first limitation. Anything that removes less than 25 tons of pollutant 1 isn't valid. So we have to come up here, and our first constraint is 0.1 x1, because it's 0.1 tons of pollutant 1 from tanning, and 0.2 tons of pollutant 2. So 0.01 x1 plus 0.2 x2 must be greater than or equal to 25. So that's minimum removal of pollutant 1. So we remove 0.1 tons of pollutant 1 from tanning waste, 0.2 tons of pollutant 1 from dyeing waste. But it must be a total of more than 25 tons of pollutant 1. Our second constraint, C2. We have 0.3 tons of dyeing waste, 0.08 tons of tanning waste, and this is pollutant 2. So we repeat the same process, but reversed because we're given it in the reverse order. So 0.08 x1 plus 0.3 x2, and it must be greater than or equal to 35 tons of pollutant 2. And that's the minimum removal of pollutant 2. So now we have our first and second constraint. Our third constraint, if we look, is that the factory has to remove at least, tanning waste process is at least twice as much as dyeing waste processed. So we have to put this into a mathematical formula that would allow us to solve our problem. So tanning waste is x1. So C3 is 2x1 must be greater than or equal to x2. Meaning for every, we have to process double the amount of tanning waste than dyeing waste. And that's ratio of tanning to dyeing waste processed. So we've, small mistake here. That's C3. So we've collected from our natural language problem, we've collected all of the relevant information in one place. And our final step is to come down here into practice problem number 4 and collect all of the relevant information in our universal format. The first step is our objective function, subject to the following constraints. And it must be greater than or equal to 25 total tons, as we saw. We repeat the process for pollutant 2. And it must be a total of 35, or a minimum of 35 tons of pollutant 2 removed. Finally, in our final section, 2x1 must be greater than or equal to x2. Oh. So once we've collected all of our relevant information here in this section, we now know that from here, and we will talk about this in the future as I keep reminding you, we can solve this problem accordingly, and we can move on and determine our optimal amounts of tanning waste to process, and dyeing waste to process in order to meet all of these requirements. So thank you everyone for listening. This is the conclusion of Lesson 9. Lesson 10 will begin, and it will be the further review of several questions that continue to build on what we've done in the past. Thank you everyone for listening. See you shortly.